morning. Welcome to day 2 for our second unit, and we're going to be talking about density today. And for this, we want to think about a couple things. We want to think about the calculations that are involved, and then ultimately about how we go about graphing this. So the first thing we want to look at is the formula for density. And density is just going to be mass divided by volume. That's also what we see as our definition. It's just mass per unit of volume. So we can think about some units that would be used with density. We want to stick with dimensional analysis when we start doing these calculations. So you don't have this in your notes, but just going through the idea of what our units that we have. When we start talking about mass, remember that mass is just how much matter is contained in any object, so how much stuff there is inside of it. And that is independent of where you are in the universe. It doesn't matter if you're here on Earth or on Jupiter, you have the same amount of matter in you. If you happen to go to Jupiter, though, you're going to weigh more because there's greater gravitational force there. So the units that we're going to be looking at are pretty much for mass, we're going to be looking at grams. Then we move on to volume, and volume, that's the amount of space that something takes up. So there's a couple things that we can think about when we think about measuring volume. If it's a solid object and it's regularly shaped, then it's pretty easy for us to just take those direct measurements and do some calculations. For example, if it was a cube, it would be length times width times height, and that'd be pretty easy for us to measure. If it's a solid object, but it's not regularly shaped, then we can go through and do something known as water displacement or volume displacement, and you use that with a graduated cylinder. We're going to be doing that tomorrow in lab, but that's for our irregularly shaped solids. And then also using a graduated cylinder, you can directly measure the volume of a liquid. So those are pretty much the three different ways that you would go about getting measurements for volume. And then this is kind of hard to see, but down here at the very bottom, remember this conversion that we have memorized already. If you want to go back and forth between volume of a liquid and a solid, you need to know that 1 milliliter is exactly the same thing as a cubic centimeter. So that's what we're remembering. Which takes us to density itself. Again, it's mass per unit volume. So the units that you would expect, I guess I didn't say anything about these units, but the units for volume are cubic centimeters, liters, milliliters, things like that. I could come up with others as well. But when you're using these units in your density formula, typically you see that solids are going to be measured in something like grams per cubic centimeter. For liquids, we usually talk about it as grams per milliliter. And then gases, since we're talking about so much more, a greater volume, you want to work with a larger sample. It's going to be grams per liter in that case. And again, you don't have this in your notes, but I just want to make sure you guys kind of have an understanding of what density is. Here it says, which block has a greater mass, A or B? What do you think? Greater mass? A, because there's more stuff in A. There's a lot more stuff right here. All of these guys we're assuming are the same atoms of each of the same element in each of those samples. So which block has a greater volume? They're the same because they have exactly the same dimensions, so they're taking up the same space. So given that, which block would have a greater density? A has a greater density because there's more mass per unit of volume. So that's what we talk about. That's what we mean when we talk about density. So now, if we were to take this particular substance right here and cut it in half, which one of those would have a, what would the relative density be of each of those halves? It'd be exactly the same because not only are you having the volume of it, but you're also having the mass. So that ratio is going to be the same. That's why we say that density is an intensive physical property. So that's one of those things that we talked about last time. A couple other fun little things to think about. You just have to think about the words that are being used to ask these questions. Which one has a greater density? 1 gallon of feathers or 1 gallon of gold? Which one has a greater density? The gold has a greater density. What has a greater volume? A gallon of feathers or a gallon of gold? Same. That was a trick question because a gallon is a gallon is a gallon, so our volume's the same. What has a greater volume? A pound of feathers or a pound of gold? feathers. In order to get a pound, you're going to need a whole bunch of feathers and not nearly as much gold. And then the last one says, what has a greater mass? A gallon of feathers or a gallon of gold? And then it's going to be your gold. Okay, so now we get down to the math that's involved. And I think somewhere in a slide that we've passed by, it probably told us, hey, make sure you're using dimensional analysis in density problems. So this first one, and I really want you guys to stick with that idea as much as possible. Sometimes it's a little bit challenging to really even think of it as dimensional analysis, but dimensional analysis really is just thinking about the final units that you want and having everything else cancel. So in this first example, the first thing I'm given are these dimensions. I'm told that a block of wood has these dimensions, centimeters times centimeters times centimeters. What variable does that give me? That's going to give me volume. If I go through that calculation, that is going to give me volume. You do not have to rewrite anything there, except it might be nice to go ahead and say volume equals, and then you plug that into your calculator. And don't round it. What do you get in your calculator? Good, thank you. So 150.88, and that's going to be in cubic centimeters. Now, I know that you guys would look at this and say, okay, well, there's 3 sig figs, 3 sig figs, 3 sig figs. So I'm going to round that to 3 sig figs. Don't round yet. Wait till the final answer of your problem. That's just going to give you the best results. So you keep that in your calculator. Our final answer will be rounded. So we know our volume. I'm just going to rewrite this. We know our mass is 71.3 grams. So now the question is, what is the density? So the way that dimensional analysis works is if you know by asking density, that really means grams per cubic centimeter. That's what we're looking for. So all you need to do is put your grams in the top and your volume in the bottom. Yeah, you just really went through solving D equals M divided by V, but we're thinking about it in terms of units. This next one will be a little bit more, it'll illustrate it a little bit better how dimensional analysis is being used, I think. But now this is not my final answer. I have to actually plug that in, and in my calculator, I get this number, but I know that I am going to round that to 3 significant figures, because here we've already said that that's 3 sig figs, and then also right here that is 3 sig figs. So my lowest number of significant figures in this given problem is 3, so this becomes 0.473 grams per cubic centimeter. There we go. All right, I'm going to keep going. Next one. Here we're looking for cubic centimeters. So what we've been doing with dimensional analysis is just kind of writing that out here to guide us. Now, I want to figure out my cubic centimeters, and I know that I'm starting with 75 grams of zinc, and the density of zinc, this is different than what we said the other day, isn't it? The density of zinc is 7.14 grams per milliliter. Maybe that's a different density based on whether it's solid or liquid. We were using an example. And we did a little demo in lab and actually happened to look it up, and it was 6.57, I thought. But here we have a different density that's given to us. In this case, if I want to find cubic centimeters, which one of these values am I going to start with? The one that has 1 unit or 2 units? 1 unit. So I'm going to start with my 75.0 grams. Now keep in mind, I'm looking at what I have in my problem, and you guys are going to get to where you just kind of jump right past this and just make this one additional step. But I'm going to do another step on top of that. I'm going to look at my problem and say, well, I've got it as grams per milliliter. So I can get rid of my grams and go to milliliters. We know that there are 7.14 grams for every 1 milliliter, because that's what that problem tells us. That's why we went ahead and started with our 1 unit because we weren't sure what was going to happen with this, with our 2 units, if our numerator or denominator was going to have to flip like this. So now that we've got it in milliliters, we get rid of the milliliters and we go to cubic centimeters. Easy conversion, but all that does is get us from volume of a liquid to volume of a solid. And as a final answer, I believe you come up with 10.5 cubic centimeters. That is it. That's probably a little refreshing for you guys after having some tougher dimensional analysis problems. That's really all there is to density calculations. So I guess a word of caution, make sure you look carefully at the units that are supplied. If it gave you kilograms and density was in grams per something, so you need to make sure that you convert appropriately. So we are done there. What did I skip? Now we're going to go ahead and talk about graphing of density. And for this, remember that when you graph this, actually let's remind ourselves first, density is just mass divided by volume. So if you think about this as being your rise over your run, when we graph this up, we are going to want to make sure that the rise is here on the y-axis, so that's going to have to be your mass, and your volume is on your x-axis. So that's how we're going to graph density. So when you get all these data points and you do your best fit line, which we're going to talk about, that best fit line, that slope, is representing your density. That's what that slope is. Okay, so we've got these rules for a good graph. You are going to do a lab on this tomorrow. And I can tell you that when I look at my grading rubric and I start grading those labs, because you're going to have to graph some things in your lab, I'm going to go through and check all of these things. You will get points off if you don't have a title, some sort of descriptive title like density of whatever. If you don't have that title on your lab, you'll get points off. If you don't label your axes, if you don't specify the units for those variables, you will get points off each time. So all of those graphs have to have that done. Choose an appropriate scale. You cannot use the little lightning bolt thing that shows that you're skipping data points that I know you guys have done in math before. So you have to show each and every one of those increments properly. When you guys go ahead and show those data points, remember how our lab notebooks with that carbon copy capability, that any tiny little pressure that you might apply to it, if you don't have that blotter in, it leaves little marks and stuff all over those pages. So because of that, when you guys do plot this up, don't just put little dots that might kind of appear anyway. What this is mentioning is you're going to put a dot with a circle around it. That way I can really tell which ones you mean to be data points. So it's just a way of being very descriptive with your graph. So you're going to have these dots that with circles around them. Those are your data points. Then what you're going to do is you're going to need to somehow represent that slope of those data points. And the way you're going to do that is with a best fit straight line. For this, you need a straight edge. Just hand drawing it is not going to be good enough. So you would get out a straight edge. I have straight edges in the drawer over there, by the way. Or you just use a book or something like that, and you are going to eyeball it and figure out where that best fit straight line is. Now, occasionally what's going to happen is you're going to have some data that doesn't create a best fit straight line, but instead has a best fit curve. So eventually, not tomorrow in lab, but eventually you'll get points that might be more like that, and you know it's going to be a best fit curve. Our calculations are also going to help us with that and understanding what's going on. So we'll talk about that here shortly. We know that our slope is going to be rise over run. And then here's the other important thing. This is going to be what we need to do tomorrow in lab, and repeatedly throughout the year you're going to need to be able to report the equation for a line. So here we see it written as y equals mx plus b. When you guys use it in your calculator, you're actually going to see there's no m. It's ax plus b is how that equation is written in your calculator. So same sort of thing, where a is going to be your slope. Now when you report this, I don't want to see y and x physically written. So that's what this is telling us. Instead of writing y and x, what we want to do is we want to write it in something known as scientific form. That's the way it's going to be phrased on your lab. Throughout the year, it's going to say, report the equation of the line in scientific form. I would put stars by this all throughout the years. People always ask me, hey, what does that mean, scientific form? So now you know. That's it. So don't forget that. In this case, what it is instead of writing your y and your x, you're going to report it in whatever variables those happen to be. So what do we know about this? What's on our y-axis? Mass. And on our x is going to be volume. So the way you would report this is instead of saying y, you would say either capital M or spell it out, mass. And then instead of having your x here, you would say capital V or spell it out as volume. And you would report the values that you get as well. Okay, so that's what this means. Make sure you know now, because I will take off points all year long if I just start seeing x's and y's instead of the actual variables that are being used. In our lab tomorrow, it's going to be volume and mass, but it could be other things throughout the year as we go on. Okay, so now I'm going to go through these things really quickly. This is not on your handout, but I just want to make sure you guys know what graphs tell us and how to read these things. So if we had a graph like this, and it asks what is the mass of 20 milliliters of this substance, you need to be able to read a graph for like the end of course exams that you guys have. So I know that in chemistry you'll be reading lots of graphs on that. It says 20 milliliters of this substance. So I'm going to come down to my volume, 20 milliliters. I go up, ooh, I even hit this data point. I go on over, and I see that it's going to be 100 grams. You could do the same thing from the opposite side. What is the volume of 150 grams? So you come on over, you hit this data point, and you come on down and see that it's 30 milliliters. You could have even done that from the data table that you might have had for this, because you had those exact data points, right? But now, what if you didn't have those exact data points? So number 3 here, it says using your graph. So we're not doing calculations. It says using your graph, what would be the volume of 250 grams of this substance? Well, 250 is up here. I didn't take those values. I didn't do any measurements back in lab that went up that high. So what I need to do is on my graph with a straight edge, I extend my line, and then I can read it. I can see that at 250 grams, I can come over here. Yeah, there's no data point, but I've got a line there, a best fit line. And I come on down, and I see that that is 50 milliliters. Actually, cubic centimeters is what I should have written. I could do the same thing here for number 5. It says using your graph, what would be the mass of 25 milliliters? Here's 25 milliliters. I come up, yeah, there's no data point there, but there's a line. I have my line there. I can come over and see it's 125 grams. So now what I really want you guys to see from this is there's a name for this type of method where you're estimating what that data would be based upon your graph. Anybody know what this first one's called, where you're going beyond your last data point? So we are going extra. We are going beyond. It's extrapolation. That's all one word. So maybe make a little note about that word. Extrapolation, it's estimating data beyond last data point. And by last data point, it could really be either side of the last or before, beyond or before. And then if that's extrapolation, extra, here in this one, it was within or between. So what do you think that's going to be? Good. Interpolation. Okay, so that's a method where we're estimating data between data points. So that's all I wanted to show you with these. Okay. And then that gets us now to where we're going to go ahead and learn how to plug this stuff into your calculator. And I think this is going to be the end of the video. Maybe I'll try and post another one that shows how to do this, but I can't use the TI emulator with this software.